Hey folks, welcome to another episode of CockroachDB Bites. So we are on episode 3 of the architecture series. And today we're going to be talking about cluster architecture. So previous one we talked about what is CockroachDB, and then after this one we'll jump into the CockroachDB software stack. Just pop this into full screen here and get a nice view, and we'll jump right into it. So this will be kind of a short session. But as I mentioned previously, the CockroachDB runs as a cluster, and a cluster is essentially just a set of nodes that are running the CockroachDB process. So you can see here on the right, we've pictured 4 nodes, and each of them has a CockroachDB process running in it. Those nodes, they might be VMs, they could be bare metal machines, they could be Kubernetes pods. It actually could be a single node like your local laptop that's running multiple instances of the CockroachDB process. You can actually simulate a cluster locally doing that. So each of these nodes really just represents a separate CockroachDB process. Now in CockroachDB, the nodes are symmetrical, meaning that there's no special or primary node. So what this means is you don't have to figure out, like, I need, X gateway nodes and Y storage nodes. Every node essentially is equal. And that is, the nodes operate with the shared nothing architecture, meaning that there's not any crossover in resources, and they're communicating primarily through gRPC calls when they communicate, and also gossip protocol. So one of the fundamental areas to understand when we are looking at the architecture is how data distribution works across the cluster and across the nodes. And in CockroachDB, data is divided into what we call ranges. And ranges are essentially logical, contiguous chunks of data. So if you think about it on a really basic level, suppose you create a table. We'll see this on the next slide. I'll go into a little more detail. But that table may exist in a single range to start, but as you start adding data to it, it may split into 2, 3, 4, etc. ranges. So those logical chunks of data are replicated 3 times by default and distributed across the cluster. So on the right, we see our 4 nodes, and we see 2 different ranges. And we can see that any given node doesn't necessarily have all the ranges. So in this 4-node cluster, we've got 3 copies of range 1 and 3 copies of range 2. But we can see that node 1 and 2 actually only have 1 replica on them. So a range has what's called a leaseholder, and that would be a replica that's responsible for coordinating read and write requests, or technically a node. And by default, when you issue a read and write request say you're doing a select on a table, maybe you're doing a key value lookup, it's going to find the range that's responsible for that, and it's going to send the request to the node with that range. So that's called the leaseholder. And there's situations where you wouldn't necessarily send the query there. You could do follower reads, for example. They wouldn't go to the leaseholder, but by default, all the reads and writes go there. And then a somewhat related concept is called a raft leader, and that's responsible for ensuring that replicas of data are maintained correctly. And as we talk, we'll sometimes use these a little bit interchangeably, leaseholder and raft leader. Really the distinction that I like to think about is that CockroachDB implements the raft consensus protocol for achieving raft quorum. We'll get into that when we start talking about the different layers of the software stack. In the raft consensus protocol, there's a role called a raft leader, and that's part of the standard consensus protocol, whereas a leaseholder has a bunch of other responsibilities that are specific to CockroachDB, like coordinating these read and write requests. So it's an optimization to place them on the same node, but there's situations where they can be on different nodes. So when we talk about leaseholder and raft leader, we might call it a leader or just a leaseholder. A lot of times we're talking about the same thing unless we're talking about like why they might be separate. And then just digging a little bit further into ranges and replicas. So table data is stored in a key value storage system. So we'll go into a little detail on what those keys look like and what the values look like. But the key is typically like a primary or secondary index key. And then the value, depending on whether or not it's a primary or a secondary index, for example, on the primary index, the value would be an encoded representation of the row. And then, as I mentioned before, ranges are stored in contiguous spans of key values. And the replicas of range are maintained on separate nodes throughout the cluster. And in a sense, when we talk about indexes, we'll talk about primary index, which is essentially the index that lives with the table data, row data itself. So they're very similar to each other. They just have slightly different key value distributions. So as an example on the right, let's say we created a dogs table and it had all these values from Carl to Z. So depending on how we have the range configured and the replicas configured, we might split that on Carl through Jack, Lady and Petey, and Pinetop and Z, and each one of those would be a separate range. And when we say insert data into that range, then we would look up the which range that data belongs to. Like if we insert a row between Carl and Dagny, then we would look that up and find a spot for it. And again, if these ranges get too big, then we would split them. If they end up being like we delete a lot of data and it gets small, we would merge them back together. So those are just a few of the high-level concepts to understand before we start really digging into the details of the software stack, which we'll be doing in the next session. Thanks for joining.